And now, how can we represent those ARMA models as first order ODEs? So we got the intuition about this chain of integrators. And this chain of integrators is going to appear once more whenever we want to take an ARMA model and write it as a first order vectorial ODEs. Watch out, the name, an alternative name for this module is how do we represent ARMA models as state space models? Because this one is what? The state space. State space is first order. True? We are going to find something like this. We take an ARMA model, we find a procedure to write it as x dot is equal to ax plus bu, y is equal to cx. This is going to be our linear time invariant system in state space. This is the one that we are going to use to build the linear quadratic regulators that we are going to use for controlling the matrix. Okay? This stuff here is very important because it's a way of writing things that enable us to do fancy controllers. And it's also a way of writing stuff such that we see that linear algebra matters for us control engineers. Okay? So, as a recap, whenever we do stuff from a control perspective, it's okay. We start where? Physical laws. With physical laws, what do we write? Acceleration is equal to velocity plus position, blah, 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 blah. Whenever we do physical laws, we get what? We get typically nonlinear systems written as a kind of ARMA. They are not ARMA, but they are nonlinear systems written with like y 4 dots is equal to stuff. Then what do? We take this one, we linearize it. Linearizing the stuff, we get ARMA. Okay? ARMA, this one, we are going to see that somehow it's not in state space. We saw it. It's going to be treatable with some tools. If we want to make a state space model, we need to do what is going to be happening in this module right now. And typically, as control engineers, we tend to prefer working with this one whenever we do advanced control. Whenever we want to do advanced control like MPC, we work with state space. Whenever we want to do PID, lead lag and stuff, kind of simpler stuff, we stop here. Okay? Are we together as a workflow, people? Physical laws, nonlinear equations, linearization, ARMA, PID stuff, advanced control, state space. This module from ARMA to state space. Okay? Together? Perfect. Blah, 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 blah. Oops. So, this is our ARMA. And we want to go to a state space. Okay. I'm going to use Laplace. Even if you didn't see Laplace, we are going to see it soon. In a certain sense, trust me, we are going to be able to write this Laplace as, this ARMA as something that looks like this one. I do it. So think of it as just a Deus ex machina thingy. We take the ARMA and we rewrite it in this way. 2 dots, perfect. Then we write s squared y. 1 dot, perfect. Then we write it as 2 times s y. 3 without dots, we write it in this way. Okay? So this one is going to become 4s squared u plus 5su plus 6u. Together, every dot becomes an s. And then it's a polynomial in S. We will see what it means later on, but don't worry for now. We write something that is like this one. True? ARMA becomes this. Because we take the polynomials in S and we put them here. Are we together up to now? S is the derivative. True? As we say that S is a derivative. Because whenever we have y dot, sorry, whenever we have y and we multiply times s, it's meaning y dot. True? And if I divide, what do? I get the integral. True? We are going to motivate this much better whenever we do Laplace transform. For now, as a placeholder, s derivative 1 over s integral. That means this stuff here. That means that whenever I write this stuff here as I was writing it before, how do I write it? I write it in a way that is slightly different. It's like y3 dots. So this one is the y3 dots. It's going to be the sum of stuff. And then it's going to be 1 over s, 1 over s, 1 over s. And whenever I do this chain of integrators, I will have y3 dots, y2 dots, y dot, y. We should add the initial conditions, but kind of in this representation that we are doing right now, they disappear for certain reasons that we are going to see better later. But you see that in a certain sense, we have a chain of integrators that leads to a chain of y's. That then I can reuse how? Minus a1, minus a2, minus a3, plus bu, ub. We got it, as before. True? Come on, solve it together, people. 1, 2, 3. So it's an operation for which eventually this stuff here, we substituted it with this and we ignore the initial condition because we are neglecting the initial conditions. Actually, what we are doing right now, by writing things in this way here, we are looking at the force response. What does it mean to look at the force response? It means that the initial conditions are set to 0. Okay? Together, that's formally why we are doing. Because we are kind of trying to find just the force response. Now, we want to write stuff in state space, true? It means x dot is equal to stuff, y is equal to stuff, true? And this has to be a vector of states. It's a bit confusing. It's a bit confusing, but I hope that you see it from a graphical perspective. A state vector is a set of information that, if I know that plus I know u, I'm able to forecast. True? Are we together on this? A state vector is something that is a state of information that plus u enables me to compute forecasts. How much are we on this, people? 1, 2, 3, because otherwise we do not know how to proceed. To compute forecast means to compute this one. True? Which information do I need? This, and the u. What will be the state vector? This, and this, and this. You see? Because having that 3 points enables me to compute the sum together with the u. I need a u. True? Okay? Are we together? What is gonna be my x? My x is gonna be, my x vector is gonna be y dot, y2 dot. From an intuitive perspective. And from a formal perspective, we can write this thing here. It's very interesting. We generate a variable xn that is going to be what? Is going to represent my ARMA part, or better, the autoregressive part of my ARMA. Whenever I write this stuff here, what am I writing? I'm writing xn times polynomial in S, that is my A of S, equals to u. True? If this one, this A of S, was S3 plus 2S squared plus 7S minus 9 is equal to u, this one eventually is xn 3 dots plus 2xn 2 dots plus 7 xn dot minus 9xn is equal to u. True? You see, it's kind of an autoregressive part with the static u, with u without the dots. True? And then whenever I take this object here, what am I doing? I'm recreating y. You see that in a certain sense, this is the definition with this Laplace that we're going to see with collecting S or using S as derivatives. Having an intuition that my state is in a certain sense deriving from a chain of integrators. Let me resay it. My state, whenever I'm going to work with ARMA, is going to be following a chain of integrators because we know how to represent ARMA as a chain of integrators. And the state is what I need to forecast. Are we together? So the states from an ARMA follow a chain of integrators. Together on this, 1, 2, 3. Perfect. I'm using this kind of trick of taking an ARMA written in Laplace and dividing into a state that is an autoregressive part plus a moving average part. That is the moving average part. How much are we together on the name moving average? What it was? 1, 2, 3? I see some twos. Sorry for going back and forth, but just to be, I want to everybody to be sure. So y at time n is equal to 7u at time n minus 2 plus, or better this way, 0.3 periodic n minus 1 plus 0.3 periodic u n plus 0.3 periodic u n plus 1. What did I write here? What is this? It's a smoothing filter. It's a medium, a mean filter, sorry. It's a filter that is non-causal. True? This is non-causal. Do you see that this is non-causal? Past and future. This is, I've got a time signal. Every time that I want to filter something, I take this, compute the mean, and substitute with the mean. True? Together? Generalizing, y is equal a sum of coefficients I, u, n minus t minus I, or the derivatives. This is a moving average. Okay? We are averaging out functions of the u's. Together? Moving average in the sense that it's an average that is moving with time of what? Functions of the u's. Are we together on the name, people? 1, 2, 3. This one is a moving average on the x. That is an autoregressive on the y. True? Now, let's focus on this stuff here. Xn, I define it as x1, the integral of xn minus 1, and, or this way here, I'm saying it in a bad way. I see that I could have said it in a slightly different way. Ignore this for now. Are we together that whenever I've got y 3 ends, then I've got 1 over s, then I've got y 2 dots, 1 over s, y dot, 1 over s, y. Think of this. This, and this are the state. True? And in a certain sense, I can think at the state as I've got an element of the state that I integrate, and I've got another element of the state, and I get an element of the state. I have a behavior of the elements of the state that each component is the integral of the previous one. Do you see that in the state that is three-dimensional, each component is the integral of this one, of the previous one? True? And here we define one variable, but we might think that eventually this variable is the integral of another one. Okay? So, what is this object here? This object here is this. And x minus 1 is this one. And in a certain sense, x minus 1 is the derivative of xn. So this one is, let's say, from a mechanical system point of view, is the position. And then I go back, velocity, I go back, acceleration, blah, 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 blah. True? Do you see it? And I get a chain that connects the various x's. You see? So this one, why did I put n? Because it's the final one. Okay, it's the final one. And then you think, you trace back. Okay, once you have this, I should have put this graph here. If I was putting this graph here, this would be very, very much clear. You see, this drawing is clear. True? 1, 2, 3. This drawing is clear. True? Perfect. Whenever I write this stuff here, I am defining the last element. That means that I can trace back all the various states by opportunely multiplied times s or s minus 1. Okay? That means this. Whenever I rewrite this stuff here, I'm writing this. Look at this plot. Tell me if you agree with me. Okay? And then, what happens? If I think at y, what is y? Y is the polynomial b times x. That means, since the polynomial b it's something with the s's, let's make an example. Let's make an example here so that it's going to be more clear. If I have y 3 dots plus 3y2 dot plus 2y dot, what time is it? We make it plus y equals to 9u2 dots minus 4u dot plus 5u. We are saying that basically, essentially, we are rewriting this as xn that multiplies s cubed together plus 3s squared together plus 2s plus 1 together is equal to u. This part here is what? This part here. Sorry, up to here. We are together? Perfect. And then we write y is equal to, now I forgot the, remember me, it's 9s squared minus 4s plus 5. It's 9s squared plus 2 bits. 4s plus 5. 5, what? xn, what's out? What's out? xn, okay? Are we together? Not you, xn. It's a moving average on the xn. If I have xn here, and I do write it in this way, this is going to be 9s squared xn minus 4s xn plus 5xn, but this is xn minus 2. Sorry, this one was x3 because we've got 3 states, so this one is x3. We have 3 states, so it's x3. This is x3. Sorry, I'm kind of dumb. 3 states, the last state, x3. True? This is x3, this is x3, this is x3. This one is going to be what? 9x1, 4x2, 5x3. Together, you see how I use the s to kind of integrate the better, derive the xn. But then at this point, what is this part here? It's this part here. Do you see it? I've got 9xn, x3, minus 4 x2 plus 5 x1. Together. And in formulas, this is interesting. This is interesting. xn minus 1 minus 2, blah, 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 x1. x1 is what? Or better, the x1 dot is what? x1 dot is u plus this stuff. x2, or better, x2 is x2, x1 is x2 dot, true? x2 is x3 dot, true? You see it? Are we together on those formulas that derive from the graphical approach? I can write them from a matricial perspective. How? Here it is. Look at this. x1 is this inner product plus u. Together, you see it? How much are we together on this, people? 1, 2, 3. Perfect. x2 dot is equal to what? It's equal to x1. True? x3 dot is going to be equal to what? x2, etc., etc., etc. You see the structure. And then we're going to have a y. The y is what? bx. Those b's is going to be this matrix C. This one is going to be my matrix A. This one is going to be my matrix B. Watch out at the notation, okay? B. Now, I write it in this way. This is a formula that at this point you might also use like this, as you might remember it, how it was derived or not. If you don't remember how it was derived, better, because it's something that is useful for later on the courses. This is called starting from an ARMA and translating it into a control canonical form. That is a state space representation, x dot is equal to ax plus bu, y is equal to cx, where A looks like this, B looks like this, C looks like this, and B looks like this. It's a very special structure. You see how it was derived. Of course, you've got to read, but you got the points. There's nothing magic here. Caveat. There are two control canonical forms. One with a matrix that opens in this way, and one with a matrix that opens in this way. The one with the coefficients here have a flipped sign. My suggestion is memorize this version here. Why? You have y and dots is equal minus a1, or better. You've got a polynomial in S, true? Here, you've got a polynomial in S, true? And you have a polynomial in B. So, if I write y several dots is equal to polynomial in S plus polynomial in B, in S. This is my AOS, this is my BOS. Are we together up to now? Do you see what I'm drawing? Perfect. From those polynomials that start from higher order and go to lower order, we write the control canonical form in the way that I'm suggesting you to do, with the same coefficients and the ones, the same coefficients, A, B, 1, 0. Those ones are those ones. Those ones are those ones. And you see that the signs kind of are the same. If you work with the control canonical form in the other way, you're going to have the A's like in this way, and the ones, and the B's in this way. Okay? It's a different way of writing the control canonical form. It's basically corresponding to say that this is x1 and this is xn. You flip all the signs. It's going to be a mess, I think. I think it's much easier to remember this formula here, because this formula here, in a certain sense, the coefficients, you see them immediately. Okay? Together? Let's make an example. Let's make a numerical example. Or you do it. Y 3 dots is equal to 3 white dots plus 2y dot minus 1y plus 9u 2 dots plus 0 plus u dot 0.5, no, 1/2 u dot. Write it in state space. How many states do we have? 3, because we have y 3 dots. So x dot ax plus bu, y cx. What is a? It's gonna be 3, 2, minus 1. What is gonna be b? 1, 0, 0. Okay, the 1 goes basically on the top row. What is gonna be c? 9, 0, 1/2. You see, immediate. You see that it's immediate. What happens if we have u's with higher dots? Non-causal system, we are not going to do in this course. Okay? Together? We are not going to treat the case where this one is equal or higher than this one. Because that's going to, actually the equal case, there is, but let's ignore it. Okay? Together? Any LTI system written in ARMA can be translated into a state space. If we have this one bigger than this one, there's other forms that we do not see in this course, but eventually boils down to something that will look like this. Linear algebra essential for control. Questions, people? Are there questions? Yeah.
In linear systems, we have been dealing now with this, but then like finding the eigenvalues instead.
We are going to talk about eigenvalues much more in 2 or 3 weeks.
Okay.
And we will see that the poles, the zeros of these and the eigenvalues are very strictly related. We are going to see very soon. Other questions? Then I think